All right, so last time we started this section on vector spaces and linear systems, and I mentioned that a better title is column space, row space, and null space, since this is what we will consider in this section. And last time we wrote down several definitions. Let me repeat them. The first one is the row space of a matrix. It is the span of the set of its rows. And the row rank is the dimension of the row space. The way we find a basis of the row space is that this is the set of rows with pivots in them. So for this we need a reduced row echelon form, or at least we need a echelon form where we can see the pivots. The second definition is the column space of a matrix, which is the span of the set of its columns. And the column rank is the dimension of the column space. The way we will find the basis for the column space is that this is the set of the original columns in the matrix that have pivots in them. Again, for this we need the reduced row echelon form to find the pivots, or at least some kind of echelon form where the pivots are showing. So a new definition that we haven't looked at before is the definition of a null space of a matrix, which is the solution set of the homogeneous system where the matrix is the system matrix. And we mentioned before that the solution set actually is a subspace in a given vector space, and we will call this subspace a null space. It's important that we have homogeneous systems for the null space. So the way we find a basis for the null space, that this will be the set of vectors in the vector parameter solution to the homogeneous system. Really, there is nothing much new in this section, since again for this null space what we need is solution to the homogeneous system, and we looked at this before. We also looked at the vector parameter form of the solution. So here is an example. Matrix A given 4 columns, 3 rows. To get the reduced row echelon form, we start with the pivots in the 1-1 entry, and we make the entries under it 0. So the new row 2 will be row 2 plus minus 2 times row 1, and the new row 3 will be row 3 plus minus 4 times row 1. With this we get the zeros here in the 2-1 and 3-1 entries, and then we go to the next pivot in the next row, second row, second column, 2 is a pivot, and we zero out the entry under it. We have to zero out 4. So for that what we do is we add to this row 3 minus 2 times row 2. And this actually zeroes out the whole third row, not just the entry under the pivot. And with this we arrive to the bottom of the matrix. Once we reach the bottom, then we go up from there to continue and zero out the entry above the pivot. We only have one pivot in the second row now, and there is nothing above the first row, so the only thing we have to zero out is the 3 above 2. For that we take the common multiple, least common multiple is 6 for 2 and 3. So we multiply the first row by 2 to get 6 there, and then the second row with minus 3 to get minus 6 there, so that they cancel out. With this, the first row becomes 2, 0, minus 11, minus 1. And then the second row is 0, 2, 3, 1. This is the echelon form, not the reduced row echelon form. For reduced row echelon form, we would need to make the leading entries 1. So we would have to divide by 2. But as I mentioned, for the column space and the row space basis, we don't really need the complete reduced row echelon form. Notice also that the reduced row echelon form, if we divide by 2, will introduce fractions like -11/2 and 3/2 and 1/2 and -1/2. So in order to avoid fraction, we can stop here for the column space and the row space. And once we have that the pivots are there in the first and the second column, and the first row and the second row, so the basis of the row space of A, again, this is the set of rows with pivots in the rows, and we can use the echelon form in this case. So we have row 1 and row 2. We have row 1 and row 2 with pivots in them. That means those two rows will form a basis for the row space. These row vectors usually are written as columns because we are talking about a basis for a space, and basis vectors are usually written in column vector format. Okay, so notice that we have the first row here and the second row with the pivot in it. So this is the basis of the row space. For the basis of the column space, these will be the columns in the original matrix corresponding to the pivots. We have pivots in the first and the second column. So we need the first and second column, but we need from the original matrix. And those are the vectors 1, 2, 4, 3, 8, 16. 1, 2, 4, 3, 8, 16. So this is the basis for the column space. The column vectors in the original matrix that have pivots in them. Finally, the null space. Null space is the set of solutions to the homogeneous system. So unfortunately, we have to continue to the full reduced row echelon form, and with the augmented matrix where you have zeros on the right hand side, since this has to be the homogeneous system with 0 right hand side. So to continue and to get the full reduced row echelon form of the matrix, we have to divide both rows by 2 in order to get 1s in the leading entries. And then, yes, this introduces fractions. Once we have the reduced row echelon form with 1s in the leading entries, we can use notation x1, x2, x3, x4 for the columns and for the variables corresponding to the different columns. And then we can write the solution, the x1 is, well, we have to rearrange it and write it on the other side. So we have to switch the sign here because these go to the other side once we solve it. So x1 is plus 11/2 x3 and plus 1/2 x4. Maybe I write down first what this equation was. x1 minus 11/2 x3 minus 1/2 x4 equals 0. And then we rearrange it to get x1 equals 11/2 x3 plus 1/2 x4. And then the second row corresponds to x2 plus 3/2 x3 plus 1/2 x4 equals 0. So rearranging this, we get x2 equals minus 3 half x3 minus 1 half x4. Notice that x3 and x4 are free variables, so we write x3 equals x3 and x4 equals x4. Then we write this in vector parameter form. Which means we collect together the x1, x2, x3, x4 components into a column vector. From x3s, we have 11 half in the first component, minus 3 half in the second component, 1 x3 in the third component, and no x3, 0 x3 in the fourth. Then for x4, we have 1 half in the first component, minus 1 half in the second component, no x4 in the third component, and 1 x4 in the fourth component. So this is the vector parameter form of the solution to the homogeneous system, and from there we just read the two vectors, collect together the two vectors, and this will be the basis of the null space for A. So typically these vectors contain fractions because we divide to get ones in the leading pivots. In order to avoid these fractions, it's possible to scale them. For example, we can multiply both vectors by 2 to get 11 minus 3, 2, 0, and 1 minus 1, 0, 2 as the basis for the null space. So these three spaces and these three bases are the important in this section: the row space, column space, and the null space. The notation for the null space is null of A, or ker A, which stands for kernel. And the dimension of the null space of A is called the nullity of A. The notation for the column space is col A, or sometimes A, which stands for image of A. Note that the row rank and also the column rank are the same because they're just the number of pivots. The dimension of the row space and the dimension of the column space both come from the pivots, number of pivots. So for that reason, there is no reason to distinguish as row rank and column rank. Simply, it's just called rank of the matrix A. Also notice that the dimension of the column space of A and also the row space of A is the number of pivot variables. So this is the rank of A, the number of pivots. The dimension of the kernel, the kernel is coming from the solution to the homogeneous system, and when we have the vector parameter form, we factor out the free variables. So that means that we have as many free variables as the dimension of the kernel of A, as the number of vectors in the basis of A. So that means that when you add together the pivot variables and the free variables, the number of them, that's the number of columns. This is called the rank nullity theorem that says that the rank of A plus the nullity of A equals the number of columns in A. Here is one more example. We have matrix A with 5 columns and 3 rows. we have a pivot in the 1, 1 entry. We make the numbers under it 0 by saying that the new row 2 is row 2 plus row 1, the new row 3 is row 3 plus row 1. So with this we get 1 minus 2 minus 1 0 minus 3. The first row doesn't change. The second row will be 0 0 minus 1 0 minus 1, and the third row will be 0 0 0 0 minus 1. Already from this form we can see the pivots. I box them with red. So these are the pivots. This is not reduced to echelon form, only an echelon form, but you can already see the pivots. The first row, first column, third column, and the fifth column. We have 3 pivots, so that means that the rank of A is 3, and we have 2 free variables, that means the nullity of A is 2. And then notice that when you add together the rank of A with the nullity of A, you get 3 plus 2 equals 5, and that's the number of columns in the matrix. Also, we can read from here the basis of the column space. These are coming from the first, third, and fifth column, but it's important that we need, for the column space, this must come from the original matrix. It's a mistake if you choose these vectors from the echelon form. We need the columns from the original matrix, so it's 1, minus 1, minus 1. The first pivot column, the second pivot column is the third column, minus 1, 0, 1. And the third pivot is in the fifth column, which is minus 3, 2, 2. So we have the 3 vectors for the basis of the column space. For the row space, it's kind of easier. It doesn't matter which row you choose, the original or the reduced echelon form or the echelon form. We do have that we have pivots in all 3 rows. So we can take these 3 rows as the basis vectors for the row space. For the nullity and the null space of A, we have to continue to get the reduced echelon form with the augmented matrix on the right hand side, the 0 vector. So what we have to do is now, starting from the bottom, because we already arrived to the bottom with the reduction, and now we have to continue back from the bottom to the top. We zero out the entries above the pivot. So what we do is, for the first row, we do row 1 plus 3 times row 3 to get 0 there. For the second row, we do row 2 plus minus 1 times row 3 to get 0. Then we get this new form, 1 minus 2 minus 1 0 0, 0 0 minus 1 0 0 0, and 0 0 0 0 minus 1 0. So we are finished with the third pivot. All we have to do is now divide by minus 1 to get 1 there in that row. Then we continue back to the next pivot, which is in the second row, and we make the entry above it 0. So for that we do is row 1 is row 1 plus minus 1 times row 2 to create 0 there. After that we can also multiply by minus 1 to get 1 in the second row's pivot. So with this we arrive to 1, minus 2, 0, 0, 0, 0 in the first row, 0, 0, 1, 0, 0, 0, and 0, 0, 0, 0, 1, 0. And this is now, finally, this is the reduced row echelon form. We have 1s in the leading entries and 0 under and above them. So at this point, we write the components down, and we solve for the pivot variables, and the other variables are free. So from the first row, that stands for x1 minus 2x2 equals 0. We get that x1 is 2x2. x2 is free variable. It doesn't have a pivot. And also x4 is a free variable. It doesn't have a pivot. x3 is easy. It just says x3 is 0. And also x5 is 0. So writing this in a vector form, we can factor out the free variables x2 and x4. And we get that we have, in the first component, we have 2x2, 1x2 in the second component, and no or 0 x2s in the rest. Then factoring out x4, we get that we have no x4 in the first component, none in the second, none in the third. In the fourth component, we have 1 and none in the fifth component. So this is the vector parameter form of the homogeneous system solution set. And then from there, we get the basis of the null space from these two vectors. That means that these two vectors span the null space. I didn't write down that this is also basis for the null space. And this is it. 3 different concepts requires reduced row echelon form, or at least echelon form, columns, rows, and the null space.